Welcome to the introduction of basic operation and troubleshooting for the Caterpillar EUI Fuel System. This presentation is a generalized introduction of the features, system operation, and troubleshooting basics for Caterpillar engines using the mechanically actuated, electronically controlled unit injector fuel system. This presentation is not intended to replace the Caterpillar Service Manual or other service publications. For detailed troubleshooting information, always refer to the latest service publications. The EUI fuel system has been used on most new 10 to 16-liter displacement models of Caterpillar electronic truck and industrial engines introduced since 1988. This fuel system provides very high injection pressures and full authority electronic control for optimal engine performance, fuel economy, and exhaust emissions. Applications include the 3176, 3196, C10, C12, and 3406E engine families. This presentation covers 4 topics: the electronic engine families using EUI, the operation of the EUI fuel system, the operation of the electronic control system, and finally, basic fuel system troubleshooting. Since its introduction in 1988, the EUI fuel system has undergone many design changes to add features and improve performance and reliability. However, the operation and troubleshooting of all EUI systems is very similar. This presentation uses a generalized example of a system with the latest features. The 10-liter displacement 3176 engine was the first Caterpillar engine to use the EUI fuel system. Introduced in 1988, the 3176 was primarily a heavy-duty on-highway truck engine, but was also used in some industrial and marine applications. In 1996, the C10 and C12 were introduced for the on-highway truck market. The same engines were designated the 3176C, 3196 for the industrial and marine markets. The C10, C12, and 3176C, 3196 engines all incorporate several major improvements, including a higher pressure EUI fuel system and improved electronic control system. Caterpillar introduced the first 3406 engine in 1973. The newest version is the 3406E, which is the 14 and 16-liter heavy-duty on-highway engine. Introduced in 1993, the original 3406E was the first 14-liter truck engine to use EUI over the former pump and line system. In 1998, a 16-liter high-horsepower version was added to the 14-liter models of the 3406E truck engine. All 3406E engines use the high-pressure EUI fuel system and advanced electronic control system, similar to the C10 and C12. The EUI fuel system is comprised of 2 subsystems, mechanical and electronic. The mechanical system consists of the low-pressure fuel supply system and EUI injectors. These components produce very high injection pressures of up to 30,000 psi and provide precise control of fuel delivery. This results in improved fuel economy and reduced exhaust emissions. The electronic control system provides full authority electronic control of all engine functions. New features include electronic speed governing, cold startup mode strategy, automatic altitude compensation, variable injection timing, and oil pressure and coolant warnings and derate. These features result in precise engine speed control, unmatched cold starting, low smoke and emissions under all operating conditions, and built-in engine protection. The EUI fuel system and electronics are virtually adjustment-free, Most changes to engine horsepower or performance characteristics are accomplished by installing new electronic software or upgraded mechanical components. To repair the system, first identify and then replace the faulty component. All system components, including the injectors, electronic sensors, harnesses, connectors, and electronic control module, are dealer serviceable. This allows faster repair times and eliminates the need to rely on the fuel system repair shop to make component repairs and adjustments. The operation of the EUI fuel system is quite different from that of previous fuel systems. In order to troubleshoot an EUI system effectively, you must have a basic understanding of how it works. To help you learn the basics of the EUI system, we'll introduce each system component and then show how these components work together. The EUI fuel system consists of 5 major components. Electronic unit injectors produce fuel injection pressures up to 30,000 psi and fire up to 19 times per second at rated speed. The fuel transfer pump supplies the injectors by drawing fuel from the tank and pressurizing it between 60 and 125 psi. The ECM is a powerful computer which controls all major engine functions. Sensors are electronic devices which monitor engine performance parameters such as pressure, temperature, or speed, and supply this information to the ECM by means of a signal voltage. Actuators are electronic devices which use electrical currents from the ECM to change engine performance. An example of an actuator is the injector solenoid. Now that we've introduced the major system components, let's discuss the operation of each component in more detail. We'll start with the mechanical components and then cover the electronic components. Diesel fuel systems use a plunger and barrel to pump high-pressure fuel into the combustion chamber. The cam lobes, push rods, and rocker arms mechanically actuate the injectors. The term EUI is actually an abbreviation for mechanically actuated, electronically controlled unit injector. Major parts of the injector include the tappet, plunger, barrel and body, nozzle assembly, and cartridge valve. The nozzle assembly consists of a nozzle spring, nozzle check, and nozzle tip. The cartridge valve consists of a solenoid, armature, poppet valve, and poppet spring. The injector is mounted in an injector bore in the cylinder head, which has an integral fuel supply passage. On older engines, the injector seated on a brass sleeve, which was swaged into the bottom of the injector bore. The brass sleeve provided a combustion seal and separated the injector from engine coolant in the water jacket. On 3406E engines, an improved stainless steel sleeve is used. This sleeve also separates the injector from engine coolant, but the injector actually does not touch the sleeve. Supply fuel is sealed above the sleeve by an external injector O-ring, and the cavity between the injector and sleeve is empty. The injector nozzle case seats directly on the cylinder head to provide a more positive combustion gas seal. The sleeve is installed with a light press fit and O-rings rather than the mechanical swaging used on brass sleeves. Increased wall thickness on the stainless steel sleeve allows the use of internal threads. These threads make sleeve installation and removal much easier. C10, C12 engines also use a stainless steel sleeve similar to the 3406E. Rather than using O-rings, this sleeve fits in the cylinder head with a light press fit and is sealed using retaining compound on the upper and lower lands. Actuation refers to the type of force used to power the plunger, which pumps the fuel out of the injector. Mechanically actuated fuel systems use a camshaft lobe and rocker arm to provide that force. The rocker arm presses down on the tappet at the top of the injector. The tappet, in turn, presses down on the injector plunger, which pushes fuel from the plunger cavity below the plunger. Fuel displaced from the plunger cavity can flow in two directions. Fuel can flow to the nozzle assembly and to the nozzle tip. However, to flow out of the tip, the injection pressure must reach about 5,000 psi in order to raise the nozzle check against the force of the nozzle spring. The fuel chooses the path of least resistance. It flows around the normally open poppet in the cartridge valve assembly to the fuel supply passage in the cylinder head. When injection is desired, the ECM sends a current to the solenoid on the cartridge valve. The current creates a magnetic field, causing the poppet to close. Fuel flow past the poppet is blocked, and pressure begins to build from the poppet through the plunger cavity to the nozzle check. When the pressure reaches approximately 5,000 psi, the force of the high-pressure fuel overcomes the spring tension holding the nozzle check closed. The check lifts off its seat and fuel flows out of the orifice holes in the nozzle tip. This is the start of injection. The rapid flow of fuel out of the plunger cavity is restricted by the very small orifice holes. Because of this restriction, injection pressure continues to rise very rapidly, even after the nozzle check opens and injection begins. Injection pressures continue to rise until the flow rate out of the orifice holes equals that of the fuel leaving the plunger cavity. Depending on engine speed and fuel delivery, this pressure ranges from 10,000 to 30,000 psi. High injection pressures promote complete combustion and lower exhaust emissions. Pushing the fuel through the orifice holes in the nozzle tip causes the fuel to atomize into droplets in the combustion chamber. Fuel droplets burn from the outside into the center. Large droplets take longer to burn and may not have time to burn completely during a normal combustion cycle. Increasing the pressure of the fuel through the orifice holes creates smaller droplets. In turn, smaller droplets burn more completely. There are 4 stages in the operation of the EUI: pre-injection, injection, spill, and fill. The first stage, pre-injection, starts with the plunger and tappet at the top of their stroke. The plunger cavity is full of fuel, the poppet in the cartridge is open, and the nozzle check is closed. Fuel leaves the plunger cavity when the rocker arm pushes down on the tappet and plunger. Fuel blocked by the closed nozzle check flows past the open poppet to the fuel supply passage in the cylinder head. As long as the solenoid on the cartridge valve is not energized, the poppet remains open, and fuel from the plunger cavity continues flowing into the fuel supply passage. To start injection, the ECM sends a current to the solenoid on the cartridge valve. The solenoid creates a magnetic field which attracts the armature. When the solenoid is energized, the armature lifts the poppet until it contacts the poppet seat. Once the poppet closes, the flow path for the fuel leaving the plunger cavity is blocked. As fuel continues out of the plunger cavity, pressure builds very rapidly. The poppet transfers this pressure through the plunger cavity to the nozzle assembly. When fuel pressure reaches approximately 5,000 psi, the nozzle check lifts off its seat and fuel flows out the tip. This is the start of injection. Injection pressure continues to build very rapidly until the same volume of fuel, pumping out of the plunger cavity, sprays from the tip. Injection occurs as long as the plunger continues to move down and the energized solenoid holds the poppet closed. When it decides that injection should end, the ECM stops current flow to the solenoid. This collapses the magnetic field holding the poppet closed. Spring and flow forces open the poppet almost instantly. High-pressure fuel can now flow around the open poppet and into the fuel supply passage. With fuel injection pressures approaching 30,000 psi, the velocity of the fuel flowing around the poppet into the 100 psi fuel supply passage is very high. This results in a rapid drop in injection pressure. When injection pressure falls to about 3,500 psi, the nozzle check closes and injection stops. This is end of injection. The extremely fast pressure drop from peak injection to end of injection reduces particulate emissions and is an important benefit of EUI. Let's review the operation of the cartridge valve, which is the heart of the EUI injector. In order to perform correctly, this valve must be able to open and close almost instantly, seal injection pressures of 30,000 psi, and prevent leakage of high-pressure fuel during injection. Containing these elevated injection pressures without leakage requires extraordinary manufacturing precision and tolerances. Any high-pressure fuel leaking past the poppet during injection is not delivered into the combustion chamber. The poppet valve opens and closes more than 500 million times during its normal wear life. The ability of the valve to function properly after hundreds of millions of cycles requires more than quality design and manufacturing. This level of durability requires proper fuel filtration to remove microscopic abrasive particles contained in the fuel. Abrasive particles smaller than 10 microns in diameter can cause accelerated wear in any high-pressure fuel system. That is why much finer filtration is being used on modern engines with high-pressure fuel systems. The difference between normal wear and excessive wear on a poppet valve seat illustrates the importance of proper filtration. On the left, you see a poppet valve seat with normal wear after extended use. Notice the condition of the sealing band on the poppet seat. While some wear is present from continued exposure to high-pressure fuel, the sealing band is still in good condition and providing a positive seal. The condition of the sealing band on the worn poppet is the result of abrasive damage from inadequate filtration. The damage to the sealing band is due to abrasive particles in the fuel flowing at high velocity past the poppet seat. This worn poppet seat leaks significantly during injection, resulting in low fuel delivery into the cylinder. In short, a prematurely worn injector. This condition can be avoided using proper filtration. Caterpillar offers high-efficiency fuel filters that meet the demands of newer high-pressure fuel systems and specifies the use of high-efficiency filters in many applications. Field experience demonstrates that these new filters more than double wear life of both new and old fuel systems over the former standard cat fuel filter. There's a good deal of confusion regarding filter ratings. One of the more common terms, micron rating, can be misleading. There may be significant differences in the ability of different brand filters with the same micron rating to remove very small abrasives from the fuel. Filter efficiency is commonly expressed in terms of nominal or absolute ratings. For example, a 5-micron nominal filter may only stop 50% of the 5-micron or larger particles striking it. In other words, every other 5-micron particle may pass through a filter with a nominal rating. Caterpillar high-efficiency filters remove more than 98% of particles 2 microns or larger. However, the rating of the filter paper means nothing if the construction integrity of the filter is faulty. In some cases, competitive brand filters constructed with leak paths allow large amounts of all size particles to pass. Caterpillar constructs its high-efficiency filters on a completely automated process, constantly testing to assure complete assembly integrity. Why is this fine filtration important? A recent study by a noted independent research agency confirmed that abrasive particles 5 to 7 microns in size cause most abrasive wear in fuel systems. These very fine measurements can be difficult to comprehend. This diagram illustrates the relative size between a single micron and a human hair, which is about 80 microns, or 35 ten-thousandths of an inch. The smallest particle visible to the naked eye, such as a speck of dust, is 40 microns. Particles as small as only a few microns can cause significant wear due to the extremely high pressures. This example shows the difference in efficiency between a Caterpillar high-efficiency filter and a typical 5-micron nominal filter. The CAT filter removes more than 98% of the 5 to 7 micron abrasive particles in the fuel. The 5-micron nominal filter only removes about half of these particles. This is assuming that the filter contains no leak paths, allowing abrasives to flow around the filter paper. Over time, these additional abrasives cause accelerated wear in any fuel system. This includes pump and line systems that operate at significantly lower pressures than EUI. Accelerated wear is more pronounced when the fuel contains unusually large amounts of contaminants. A good example of this problem occurred several years ago in a logging application. The customer operated log skidders with pump and lines fuel systems and complained that the fuel injection pumps were wearing out in as little as 2,000 hours. Subsequent investigation revealed no manufacturing defects, so abrasives in the fuel were suspected. The customer was using the standard Caterpillar 15-micron filter, so many of the abrasives were smaller than 15 microns. Testing the theory, which states very small abrasives are at fault, a side-by-side test was run with completely rebuilt pumps on the two identical machines. One machine remained equipped with the standard 15-micron filter, while the other machine was equipped with a high-efficiency 2-micron filter. Instead of changing filters at the recommended 250-hour change interval, both machines ran to 1,000 hours to see if the finer filter would plug from extended use. It didn't. After 2,000 hours of use, both pumps were disassembled and inspected. The pump using the 15-micron filter suffered significant abrasive wear, while the one using the high-efficiency filter looked and performed like new. These findings led to the testing of the high-efficiency filter in other severe applications around the world. In some countries, fuel lubricity is poor, and the fuel is loaded with very small abrasive particles. In these severe applications, the average life of many unit injectors in excavators has been about 1,500 hours. In extreme cases, injectors have worn out in as little as 200 hours. Since the introduction of high-efficiency filters in these applications, there has not been a single case of a documented system wear-out. Follow-up investigation shows some former problem machines now have over 5,000 hours of operation with no sign of injector wear. There are many other examples of dramatic improvements in fuel system life using high-efficiency filters. The improvements have been so significant that this filter is now the standard fuel filter for all Caterpillar products. Industrial or marine applications, where large amounts of water may be in the fuel, may have water separators in place of the primary fuel filter. The use and regular maintenance of a water separator is highly recommended where water contamination of fuel is a common problem. Water contamination is not usually as big a problem in on-highway truck applications that use fuel from reputable truck stops with very high fuel turnover rates. It is more of a problem for applications fueling out of stationary tanks with lower turnover rates. Fuel stored for prolonged periods has a much greater probability of generating condensation. The number one cause of injector failure due to plunger seizure is ingestion of large quantities of water in the fuel. All diesel fuel contains some dissolved water, normally about 0.1% by volume. We're not talking about this quantity of water. We're talking about large concentrations, in pints, quarts, or gallons, generated from condensation or tank leakage. The film strength of the diesel fuel separates the metal surfaces of the injector plunger and barrel. When the film is penetrated, metal-to-metal contact occurs between the plunger and barrel, resulting in plunger seizure and injector failure. Water has a much lower film strength than diesel fuel. Large quantities of water provide very poor plunger lubrication and film strength and lead to injector failure. Some styles of aftermarket combination fuel filters and water separators recommend removing or bypassing the factory-installed secondary fuel filter. Removing or bypassing the 2-micron secondary filter is not recommended by Caterpillar. The use of aftermarket filters, the use of competitive brand filters, or even bypassing the factory secondary filter does not void the engine warranty. However, the warranty on fuel system components does not cover abrasive wear from improper filtration, unless a defect in material or workmanship is found in the fuel system component. Over time, abrasives in fluids can cause significant wear to even the most durable objects. Proper filtration is an essential factor in the life of all fuel system components. The fuel transfer pump is a gear pump that pulls fuel from the tank and pressurizes it to supply the injectors. The pump has an internal relief valve that controls maximum system pressure between 60 and 125 psi, depending on engine model. The hand priming pump, located on the filter base, contains a check valve that allows pumping fuel around the pump gears. The transfer pump is not serviceable. Replace as a unit if it can't produce adequate pressure. Always check the service manual for the correct pump pressure specification. Most fuel transfer pumps are located on the lower left side of the front cover. They may be mounted on either the front or the back of the front cover, depending on engine arrangement and packaging considerations. The fuel filter base provides a mounting stud for the spin-on fuel filter and also contains the hand priming pump and a valve to bleed air from the system after filter changes. The priming pump and bleed valve provide a means to fill new filters with fuel and purge air from the low-pressure fuel system. Caution: never pre-fill the fuel filters at installation. Pre-filling bypasses the filter element and introduces dirt into the system. This practice alone contributes to premature system wear. The final component in the low-pressure fuel system is the pressure regulator valve. This valve is located on the outlet end of the cylinder head fuel supply passage and is a normally closed pressure relief valve. There are two styles of valves used, 3406E and C10-C12. The 3406E regulator has a simple spring-loaded pressure relief valve that only opens when fuel pressure reaches the relief pressure setting. The C10-C12 style valve has a spring-loaded poppet with two orifice holes in the end. This valve allows fuel to return to tank at a rate of 4 liters per minute, assuring adequate bypass flow and injector cooling. The pressure regulator valve also acts as a spring-loaded one-way check valve. The valve opens at 60 psi to allow excess supply fuel to return to the tank. When the engine is off and supply pressure drops to 0, the valve closes, preventing fuel in the head from draining back to the tank. While these valves differ slightly in design and operation, they serve the same purpose. EUI injectors take low-pressure supply fuel and pressurize the fuel between 10,000 and 30,000 psi. A camshaft-operated rocker arm pushes down the injector tappet and plunger, supplying the mechanical energy required to pressurize and pump the fuel from the injector. The combustion chamber receives pressurized fuel in the correct quantity and at the correct injection timing. The extremely high-pressure fuel flow through small orifice holes in the tip causes the fuel to atomize into microscopic droplets that burn more completely. This improved combustion more efficiently uses the heat energy of the fuel, resulting in improved fuel economy and reduced exhaust emissions. The low-pressure fuel system supplies fuel from the tank to the injectors. This system has three basic functions: to supply fuel to the EUI injectors for combustion, to supply extra fuel flow for cooling of the injectors, and to supply extra fuel flow to remove air from the system. The major components in the typical low-pressure fuel system are the vehicle fuel tank, the fuel transfer lines, the primary fuel filter or water separator, the fuel transfer pump, the secondary fuel filter and priming pump, and the pressure regulator valve. There are often component differences between the fuel tank and transfer pump on different engine arrangements and applications. For example, the recommended arrangement for most truck engines utilizes a 15 to 30 micron primary filter to catch large debris from the fuel tank. However, some truck manufacturers do not install a primary filter and instead rely solely on the secondary filter. Fuel drawn from the tank flows to the primary fuel filter or water separator. The primary filter screens large debris before the fuel flows to the inlet side of the fuel transfer pump. This is a simple gear pump containing an integral pressure relief valve. Fuel pressure is typically limited to between 60 and 125 psi. Excess fuel flows from the pressure relief valve on the outlet side of the pump through an internal passage to the inlet side of the pump. Fuel flows from the outlet port of the transfer pump to the secondary fuel filter. In the past, secondary filters typically had 10 to 15 micron ratings. Most 1999 and newer engines use 2 micron fuel filters. The 2 micron filter removes the very small abrasive fuel contaminants which cause premature wear out of the injectors. The fuel filter base also contains a hand-operated fuel priming pump. The purpose of the priming pump is to refill the system with fuel and remove air from the low-pressure fuel supply system after a filter change or injector replacement. The priming pump pulls fuel from the tank, around the transfer pump, and into the filter. It then pushes fuel through the supply passage in the cylinder head and back to the tank. Fuel flows from the secondary fuel filter to the supply passage in the cylinder head. On the 3406E, the fuel supply passage is a drilled hole extending from the front to the back of the cylinder head. On the C10, C12, a manifold on the side of the engine supplies fuel to each injector and returns excess flow back to tank. Excess fuel flows into the fuel pressure regulator. The fuel pressure regulator consists of a spring-loaded check valve. This pressure relief valve opens at approximately 60 psi and regulates pressure in a range of 60 to 125 psi. When the engine is off and no fuel pressure is present, the spring-loaded check closes to prevent the fuel in the cylinder head from draining back to the tank. Retaining fuel in the head maintains a supply of fuel for the injectors at engine startup. Most 1999 and newer EUI engines use a new electronic control system. This state-of-the-art system has many features and benefits. Although this presentation focuses on major electronic engine component operation, some basic electronic diagnostics are covered in the diagnostics portion of this presentation. The electronic control system consists of three types of components: input, control, and output. Sensors constantly monitor engine operating conditions and relay that information back to the electronic control module. The ECM is the computer that controls the engine. It has three main functions. It provides power for the engine electronics. It monitors input signals from engine sensors, and it acts as a governor to control engine RPM. It also stores engine operating information such as faults, events, and cumulative operating hours. The personality module is the software in the ECM, which contains the specific maps that define power, torque, and RPM of the engine. The ECM sends electrical currents to output devices to control engine operation. The heart of the electronic system is the new electronic control module. This powerful, state-of-the-art computer controls all engine functions, providing excellent performance and fuel economy while meeting stringent and ever-changing exhaust emission standards. The ECM provides many electronic features, including full authority electronic engine control, logging of engine faults, improved electronic engine diagnostics, electronic cruise control, programmable electronic PTO, engine monitoring and protection, and more than 100 programmable features. The new ECM has two 70-pin harness connectors, the engine harness connector and the vehicle harness connector. Older engines used an ECM with two 40-pin connectors. The engine harness connects the ECM to all of the sensors and actuators, including the EUI injectors. The vehicle harness connects the ECM to the engine control portion of the main vehicle harness. This includes the accelerator pedal position sensor, vehicle speed sensor, transmission, brake and clutch switches, cruise control and PTO control switches, data links, check engine and warning lights, engine retarder switches, speedometer and tachometer, and cooling fan solenoid. This wiring may seem complicated, but it's really quite simple. All of it is made up of many simple circuits. We will cover some of these circuits in the electronic system operation portion of this presentation. Sensors are simple electronic devices that detect and convert a change in pressure, temperature, or mechanical movement into an electrical signal. There are four basic types of sensors: pressure, temperature, position, and speed. A pressure sensor measures changes in pressure and sends a variable DC signal voltage back to the ECM. Pressure sensors have three wires. The first wire supplies voltage from the ECM to the sensor, providing power for sensor operation. This supply voltage is precisely controlled to 5 plus or minus 0.5 volts. The second wire is a ground wire from the ECM to the sensor that provides a 0 volts reference. The third wire is a signal voltage from the sensor to the ECM. This signal voltage varies with changes in the pressure of whatever the sensor is monitoring. The operating range of the signal voltage is slightly greater than 0 volts and slightly less than 5 volts. A typical operating range for signal voltage is 0.5 to 4.5 volts. The ECM also determines if a sensor is shorted or open by monitoring the signal voltage. If the signal voltage is the same as supply voltage, the ECM knows the sensor or sensor circuit is open. If the signal voltage is 0, the ECM knows the sensor or sensor circuit is shorted. If the ECM senses either a short or an open circuit, it will indicate a fault for that circuit to assist in troubleshooting. The key pressure sensors on the engine are the boost pressure, atmospheric pressure, and oil pressure sensors. A temperature sensor measures temperature and uses only two wires. Temperature sensors change resistance as temperature changes. The ECM reads the resistance value and converts it to a temperature. The ECM determines if the temperature sensor is open or shorted by monitoring the resistance value. If there is a short, the resistance value is near zero. If the sensor circuit is open, the resistance value is very high. The important temperature sensors on the engine are the coolant temperature sensor, the intake air temperature sensor, and the fuel temperature sensor. The third type of sensor is a position sensor. An example of a position sensor is the accelerator pedal position sensor. This sensor monitors the position of the accelerator pedal and converts that position into a pulse width modulated signal that is sent back to the ECM. A position sensor has 3 wires. The first wire supplies voltage from the ECM to provide power for sensor operation. The supply voltage for the accelerator pedal position sensor is 8 plus or minus 0.5 volts. The second wire is a ground wire from the ECM to the sensor that provides a 0 volts reference to the sensor. The third wire is a signal voltage from the position sensor to the ECM. The accelerator pedal position sensor generates a pulse width modulated signal, which is a square wave. A square wave is either full voltage or 0 voltage, on or off. Duty cycle is the percent of on time. The duty cycle for the low idle accelerator pedal position is between 10 and 22%. Duty cycle at the high idle accelerator pedal position is 75 to 90%. The accelerator pedal position sensor transmits this duty cycle signal to the ECM at a constant frequency. This type of sensor provides a very accurate signal to the ECM with a smooth transition during acceleration and deceleration. The ECM determines if the accelerator pedal position sensor is faulty by monitoring the duty cycle. If the duty cycle is less than 5% or greater than 95%, the ECM will log an active fault. The fourth type of sensor is a speed sensor. The speed timing sensor has a permanent magnet and a coil of wire. A change in the magnetic field of the sensor induces a voltage into the sensor. The ECM reads the increase and decrease in voltage as a signal. As the camshaft gear rotates, signal teeth cast into the gear pass through the magnetic field of the speed timing sensor. The sensor generates a signal voltage as each timing tooth passes. The ECM counts the time between these signals to determine how fast the engine is running. All of the teeth are evenly spaced except one pair, which has an additional tooth between them. This additional tooth sends an additional signal, which indicates top dead center to the ECM. Because speed sensors use an internal magnet and coil to generate a signal voltage, they do not require a supply voltage from the ECM. They also use only 2 wires instead of the 3 wires used on pressure and position sensors. Newer engines use dual speed sensors, each with 2 wires. One is for the camshaft gear and the other is for the crankshaft gear. Older engines use a single 3-wire speed sensor for the camshaft gear. On the dual sensor system, the camshaft gear is used to determine injector timing during engine startup. After starting, the crankshaft signal is used because it provides a more accurate and stable timing signal. With the new dual sensor system, if a sensor fails, the ECM will log an active fault and the engine will continue to run. With the older single sensor system, the engine will not run if the speed sensor fails. In review, 4 basic sensors govern engine operation: pressure, temperature, position, and speed sensors. The electronic systems on the engine may seem complicated. However, once you understand how these basic types of sensors work, the operation of individual circuits becomes much easier to understand. Another electronic feature we will discuss is called electronic trim, or E-trim for short. This feature electronically adjusts the performance of individual injectors to reduce the fuel delivery variability of a set of injectors. E-trim is necessary because there's no way to mechanically adjust fuel delivery on an EUI injector. An assembled injector must fall within a specified delivery tolerance when it is assembled and tested. However, in a set of 6 injectors, the combined delivery variability may cause undesirable idle quality or rated performance. E-trim reduces injector set variability by using a programmed increase or decrease in the current duration to the solenoid when the injector is fired to increase or decrease fuel delivery. The E-trim value of each injector is determined by injector performance at final test. If delivery is higher or lower than the exact desired delivery value, an E-trim code is assigned to compensate for the variability. When the injectors are installed in a new engine, the E-trim value of each injector is programmed into the ECM. This feature has greatly increased customer satisfaction and engine performance. When an injector is replaced in the field, a new E-trim value must be programmed into the ECM for that injector. On the 3406E, the code for the new injector is a 4-digit code engraved on the injector tappet. On the C10, C12, the trim code is located on the solenoid. This procedure is explained in the service manual and is discussed in the diagnostic section of this presentation. E-trim is used on most newer engines, including the C10, C12, and 3406E. The speed timing circuit is the most important of all the basic circuits. This speed timing signal tells the ECM the position and speed of the engine camshaft and crankshaft. The ECM requires these signals to govern engine operation. The speed timing signal is so important that it has 2 sensors, a camshaft sensor and a crankshaft sensor. Each sensor has a different advantage. The camshaft sensor provides a clear signal identifying engine top dead center. However, due to dynamics of the front gear train, there is a slight amount of timing variability when using the camshaft signal only. The crankshaft sensor provides a more accurate timing signal because it reads directly off the crankshaft. Yet it cannot determine if the engine is on the power stroke or exhaust stroke. The engine will continue to operate if either sensor fails. If the ECM detects a loss of RPM signal from one sensor, it will automatically switch to the other sensor and indicate both an active and a logged fault. The ECM will delay lighting the check engine light after detecting a sensor failure because the engine will continue to operate without loss of performance. However, the ECM does immediately indicate the fault, so the service technician can find and repair the problem. In case of a camshaft sensor failure, the engine may crank longer before starting. Since the crankshaft sensor cannot determine the power or exhaust stroke, a strategy in the ECM alternates injection timing every 2 seconds of cranking until the engine starts. The accelerator pedal position sensor circuit determines desired engine speed by sensing the position of the accelerator pedal and sends a pulse width modulated signal back to the ECM. The ECM then compares desired engine speed to actual engine speed, determining how to fire the injectors. The operator selects an engine speed with the accelerator pedal. The position of the accelerator pedal generates a pulse width modulated signal, which the ECM translates into the desired engine speed. The ECM then compares the desired engine speed to the actual speed, determining if the injectors should deliver more or less fuel. The ECM increases the duration of the current to the injectors, delivering more fuel and increasing engine speed if the actual engine speed is lower than desired. If the actual engine speed is higher than desired, the ECM decreases duration to reduce fuel delivery. With less fuel, engine speed drops very rapidly until actual engine speed matches desired speed. The ECM uses many other sensor inputs besides the accelerator pedal position signal to determine the correct operation of the EUI injectors. The ECM must determine three things to control injector operation: injection timing, or when injection starts, the quantity of fuel injected, and engine speed, in order to determine current duration and length of injection. All sensor inputs are compared to the software maps in the ECM, and output signals are sent to the injectors. These output signals control actual engine operation. The boost pressure sensor measures boost pressure in the intake manifold and sends a DC signal back to the ECM. The ECM uses the boost pressure signal to limit fuel delivery and prevent overfueling and black smoke. This serves the same function as a mechanical fuel-air ratio control. The atmospheric pressure sensor measures atmospheric pressure in order to compensate for altitude. It sends a DC signal back to the ECM. The ECM uses the atmospheric pressure signal to adjust timing and fuel delivery, maintaining engine performance and emissions at high altitudes. The atmospheric pressure sensor is also used to automatically calibrate the other pressure sensors. The engine oil pressure sensor measures the pressure of the engine lube oil and sends a DC signal voltage back to the ECM. The ECM uses the oil pressure signal to help determine if the engine is operating with low oil pressure. Every engine is equipped with an engine monitoring system that can be programmed to off, warning, derate, or shut down. The ECM will turn on a warning lamp when a low oil pressure condition exists. If the ECM is programmed to derate, engine power will be reduced. If programmed to shut down, the engine will shut down. This shutdown option is not available on earth-moving vehicles. Diagnostic codes logged will be low oil pressure or very low oil pressure. The coolant temperature sensor measures the temperature of the engine coolant. It converts temperature into a resistance value that the ECM reads. The ECM uses the coolant temperature signal to help determine proper injection timing. If coolant temperature is below a certain point, the ECM engages the cold mode strategy. Cold mode is an electronic strategy which retards injection timing to improve cold performance and reduce white smoke. Engine performance is slightly impaired during cold mode operation due to retarded injection timing. When the engine warms up to near normal operating temperature, the cold mode strategy is disengaged and normal performance strategy resumes. The ECM also uses the coolant temperature signal for high temperature protection. Every engine is equipped with an engine monitoring system that can be programmed to off, warning, derate, or shut down. The ECM will turn on a warning lamp when a high temperature condition exists. If the ECM is programmed to derate, engine power will be reduced. If programmed to shut down, the engine will shut down. This shutdown option is not available on earth-moving vehicles. There are diagnostic codes for high engine temperature and very high engine temperature. The intake air temperature sensor measures the temperature of the air entering the intake manifold. It converts temperature to a resistance value that the ECM reads. The ECM uses the intake air temperature signal to help determine proper injection timing and engage or disengage the cold mode strategy. High intake air temperature will turn on a warning lamp if the electronic monitoring system is programmed to warning, derate, or shut down. However, high intake air temperature will not cause the ECM to derate or shut down the engine. Diagnostic codes are high intake air temperature and very high intake air temperature. The fuel temperature sensor measures the temperature of the fuel in the supply passage of the cylinder head. It converts temperature into a resistance value that the ECM reads. The ECM uses the fuel temperature signal to help determine the proper quantity of fuel to inject. The volume of fuel expands as the fuel gets hotter. As engine temperatures increase, the combustion chamber requires a greater volume of fuel to produce the same level of power. Software maps in the ECM adjust injector duration and increase fuel delivery to compensate for increasing engine temperatures. The ambient air temperature sensor is an OEM-installed option which measures outside air temperature on applications which use a programmed idle shutdown feature. The sensor converts temperature to a resistance value that the ECM reads. The ECM uses the ambient air temperature signal to help determine if a programmed idle shutdown can be overridden if ambient air temperatures are extremely hot or cold. The most common use is on trucks where an operator may need to leave the engine running to operate the air conditioner or heater during a rest period. This sensor is an optional feature. The coolant level sensor is an OEM-installed option which monitors the level of the engine coolant in the radiator. It is a sensor that acts like a switch. When covered with coolant, it sends a high signal voltage back to the ECM. When the sensor is not covered, indicating low coolant level, it sends a low signal voltage. The ECM also uses the coolant level signal for low-level protection. Every engine is equipped with an engine monitoring system that can be programmed to off, warning, derate, or shut down. The ECM will turn on a warning lamp when a low coolant level condition exists. If the ECM is programmed to derate, engine power will be reduced. If programmed to shut down, the engine will shut down. This shutdown option is not available on earth-moving vehicles. There are diagnostic codes for low coolant level and very low coolant level based on how long the condition exists. Understanding the basics of how the fuel and electronic control systems operate is essential to identifying system problems. The objective of this section is to introduce the basic diagnostic procedures used to identify and correct problems on EUI-powered engines. The system used in this presentation is only an example of a typical modern EUI system. There are many different engine arrangements and applications. For example, older engines use an ECM with two 40-pin connectors rather than the newer 70-pin version. However, the basic troubleshooting logic and procedures are very similar for all EUI engines. Always refer to the correct service manual for the latest repair and diagnostic information. Modern electronically controlled engines offer improved diagnostic capability over older mechanically controlled engines, but they are not totally self-diagnostic. In order to troubleshoot an electronic engine effectively, service technicians must have 5 skills. They must be able to understand how the fuel system and electronic control systems operate, find appropriate information in the Caterpillar service manual, perform basic mechanical tests, perform electronic system tests, and interpret test results to find the root cause of a problem. A good basic understanding of system operation is the most important part of effective troubleshooting. For example, adjustments to horsepower or performance characteristics are made by installing new software or by upgrading mechanical components. No mechanical adjustments can be made to any part of the EUI fuel system. Technicians who do not understand how components and systems operate end up guessing at which component to replace. Replacing the wrong component increases customer downtime, repair cost, and customer dissatisfaction. In addition, never disassemble EUI fuel system components in the field. Disassembly generates thread debris and introduces dirt, causing serious injector damage. Unauthorized disassembly of warranty components will result in reduced or non-allowed warranty reimbursement. A second important skill is the ability to use the Caterpillar service manual effectively. The service manual has 3 parts: engine, troubleshooting, and maintenance. Under the Engine tab, you will find 3 modules: Specifications, Systems Operation, Testing and Adjusting, and Disassembly and Assembly. In the Specifications module, you will find torque values, torque sequences, pressure settings, and numerical values for adjustments, such as valve lash settings. In the Systems Operation, Testing and Adjusting module, you will find explanations of how mechanical systems operate, test procedures for mechanical components, and adjustment procedures for mechanical components, such as the valve lash settings. In the Disassembly and Assembly module, you will find removal and installation procedures for major components, such as EUI injectors, disassembly and assembly procedures for serviceable components, like water pumps, and disassembly and assembly procedures for the basic engine. Under the Troubleshooting tab, you'll find an electrical schematic and a troubleshooting module. The schematic contains location and identification information for engine wiring, connectors, electrical components such as switches and relays, and electronic components such as sensors and the ECM. The Troubleshooting module contains all of the information for troubleshooting electronic engines. Topics that are covered are troubleshooting, electronic system overview, programming parameters, troubleshooting without a diagnostic code, troubleshooting with a diagnostic code, and a diagnostic code list. In the Operation and Maintenance Guide, you will find maintenance information that is primarily intended for the operator or owner. This guide contains specifications for cooling, lube, and fuel systems, recommended practices for engine operation, and maintenance recommendations, such as maintenance schedules and refill capacities. The next important skill is to be able to perform basic mechanical tests correctly. This includes being able to measure hydraulic pressure, use a volt-ohm meter to perform basic electrical tests, checking boost pressure and exhaust restriction to determine if the engine performs properly. It is also essential that you use and understand the features in Caterpillar Electronic Technician, or ET for short. ET is required to service electronic engines. With it, you can identify, understand, and correct active faults, logged faults, and logged events. You can also read and change programmable parameters and view status screens. You can perform the injector solenoid test, the cylinder cutout test, and several other special tests that enable and disable specific ECM outputs. In order to better understand these tests, the cylinder cutout and solenoid test are performed and explained in the diagnostic section of this presentation. Finally, interpreting test results to find the root cause of a problem is critical. This includes being able to evaluate component performance of the sensors, actuators, injectors, and associated wiring. It also includes being able to understand how components and systems interact, how components work correctly, and how the system reacts if a component is faulty. These skills are important to be able to quickly identify and correct problems on electronically controlled engines. Only electronically controlled engines constantly meet demands for improved performance, reduced emissions, and improved fuel economy. There are many misconceptions about what electronically controlled engines can and cannot do. A quick review of these will illustrate why the troubleshooting skills just mentioned are so important. Electronically controlled engines can indicate active faults, log faults, and events, identify major component failure, and identify sensor and actuator short and open circuits. Electronically controlled engines cannot troubleshoot themselves, identify marginal component performance, or identify inaccurate sensor readings. In short, electronically controlled engines cannot think for themselves. It is your ability to think and understand how engine components and systems work together that allows you to perform effective troubleshooting. Performing the basic electronic tests on EUI engines is simple. The electronic diagnostic tool used to perform these tests is the Caterpillar Electronic Technician, or ET for short. ET is actually a software package run on a laptop computer. ET can perform the injector solenoid test, cylinder cutout test, identify active faults, logged faults, and logged events. ET can display engine configuration, change customer programmable parameters, flash program new software into electronic engines, and print configuration and test results for further analysis. Older engines were equipped with replaceable personality modules. Installing new software required ordering and installing a new personality module. This method increased both product cost and customer downtime. Newer ECM designs contain an integral personality module, which is not replaceable, but can be flash programmed. ET is required to flash program both new and older engines. This example uses ET to demonstrate the basic electronic tests with the screens and cursor commands to perform each test. It does not cover the actual instructions on how to use ET. Specific instructions are available in the Caterpillar Service Tool Software User's Manual for CAT Electronic Technician, form number NEHS 0679. The first diagnostic test identifies active fault codes, or active faults for short. Active faults indicate a system malfunction or problem currently present. An example is a shorted or open sensor, wire, or circuit. Let's look at an example. When no active faults are present, the ET screen will read "No active codes." If we unplug the oil pressure harness connector, ET identifies this as an open circuit, active fault, after a few seconds. The code for this fault is 100-03, which ET defines as an oil pressure sensor, open circuit. Detailed information for troubleshooting this code is in the troubleshooting guide. When logged faults are not present, the ET screen reads "No logged diagnostic codes." The oil pressure sensor open circuit fault has occurred 10 times. The first occurrence was at 3 hours, and the last occurrence was at 27 hours. The diagnostic clock indicates the total number of hours on the engine, in this case 27 hours. The ECM can remember up to 256 occurrences of a logged fault. If the fault occurs more than this, the ECM will remember the last 256 occurrences. However, after 100 hours, most logged codes are deleted. Generally, logged events are not electronic problems, but indicate an abnormal engine condition. Examples of logged events are a programmed idle shutdown, engine overheat, or engine overspeed. These are not electronic problems, but are abnormal operating conditions. The purpose of the injector solenoid test is to make sure there are no open or short circuits in the injector wiring harness and all of the injector solenoids are working. Select the Start button at the bottom of the screen to begin. ET instructs the ECM to actuate each injector solenoid in order from 1 through 6. This test will continue until clicking the Stop button at the bottom of the screen. If a short or open circuit is detected, the fault will be listed on the screen and the defective circuit will not work. The cylinder cutout test measures the contribution of individual cylinders, compares one to another, and determines if any are weak. The automated multiple cylinder cutout test, used in ET version 2.4 and later, has 3 options. First is the single cylinder cutout test. This is an optional test because it is the least effective of the 3. Only use the single cylinder test when engine performance is so poor that the engine will not continue to run with multiple injectors turned off. The second test is the 4-cylinder cutout test, which is recommended for most applications. The purpose of this test is to increase the load on the 2 running injectors by turning off the other 4 cylinders. This test shuts off half of the engine at a time and then tests 1 cylinder in the running half. For example, the test starts by turning off cylinders 4, 5, and 6. The test then turns off number 1 and samples the injector current duration to cylinders 2 and 3. After the test on cylinder 1 is complete, number 1 is turned back on and the engine stabilizes for 5 seconds before testing number 2. After 5 seconds, the test turns off number 2 and samples the injector duration of the 2 running cylinders 1 and 3. After completing cylinder number 2, the process is repeated for cylinder number 3. When the number 3 cylinder test is complete, ET turns on all 6 cylinders and allows the engine to idle normally for 5 seconds. Then it shuts off cylinders 1, 2, and 3, repeating the test sequence for cylinders 4, 5, and 6. This is the recommended test procedure for most applications. In rare instances where the 4-cylinder cutout test may not be sensitive enough to identify a single weak cylinder, the 5-cylinder cutout test may be used. This test turns off all of the cylinders except the one being tested and requires the injector to deliver a high fuel rate. The 5-cylinder cutout test is only recommended if the 4-cylinder test is not effective and is not used on all applications. The new cutout test also has some new parameters to increase test accuracy. For the test to work properly, warm the engine to a normal operating temperature. The new automated cylinder cutout will not allow the test to start if the coolant temperature is below 171 degrees Fahrenheit. The second new parameter is engine speed during the test. The test is run at either 800 RPM, 1000 RPM, or programmed low idle. If engine speed is manually changed beyond the prescribed range, the test will not start, or will abort if in progress. Accessories that put an intermittent load on the engine should be disabled during the test. Air compressors and air conditioning compressors, which can cycle on and off, will add to test variability if they cycle on and off during the test. ECM-controlled cooling fans are turned on and left on throughout the entire test. The 4-cylinder cutout test begins by the technician setting engine speed to the requirement stated on the ET screen. Once selected, this speed is maintained throughout the test. If it is changed, the test will abort. The ET software then turns off 4 injectors at a time. The remaining 2 cylinders must then produce more power to maintain the 1000 RPM idle speed. After the idle has stabilized, the ECM measures the average duty cycle of the solenoid current to the 2 working injectors. The ECM then assigns a test value to the injector being tested. This cycle automatically repeats for each injector. Listen to the sound of a test on a properly operating engine. In order to reduce test variability and make it more accurate, the test repeats 2 times and the results averaged. Once all 6 cylinders have been checked 2 times each, test values are assigned to each cylinder. The ET software completes the calculation and identifies which injectors are OK or not OK. If a new injector is installed, the eTrim code for the new injector must be programmed into the ECM. This is easily done with ET. First, go to the ECM summary screen shown here. Then select Service, Calibrations, Injector Codes Calibration. Select the cylinder number in which the new injector was installed. In this case, it was cylinder number 3. The code shown for cylinder 3 was the eTrim code for the previous injector. On the 3406E, the code for the new injector is a 4-digit code engraved on the injector tappet. On the C10, C12, the trim code is located on the solenoid. Double-click on cylinder 3 and the Change Parameter Value screen appears. Enter the eTrim code for the new injector and click on OK. A follow-up screen will ask for confirmation that the new code is correct. Click Yes and the new code is programmed into the ECM. This is all that is required to enter a new eTrim code for a replacement injector. Under the Diagnostics, Diagnostic Test, Special Tests menu, there are up to 14 additional tests. These tests are used to actuate specific ECM outputs to determine if the ECM is working properly. A few examples of these tests include cooling fan on-off. This turns the cooling fan ECM output on and off. PTO switch on lamp. This turns the PTO lamp on and off. Tachometer test. This sets the tachometer to 1500 RPM. 55 miles per hour speedometer test. This sets the speedometer to 55 miles per hour. The technician is instructed to connect one lead of a test lamp to the ECM output and the other lead to battery positive or ground. The ECM output then powers the test lamp. Caution: a multimeter cannot be used in place of a test lamp. The ECM output must drive a load, such as a lamp. This completes our discussion of basic diagnostic tests. A review of the most common customer complaints reveals the actual cause of the problem. Most injectors replaced under warranty are returned to the factory to determine the cause of failure. The process used to evaluate returned injectors is warranty analysis. This process consists of 3 major steps. The first step is a complete visual inspection. This inspection looks for signs of external damage caused by the following problems: burned solenoid terminals from loose connections, loose solenoid terminals from over-torquing, injector tip or nozzle case damage from engine overheat or improper assembly, rust or signs of water ingestion from the fuel supply, damage from improper injector removal, parts handling, or return shipment. The next step is a thorough injector performance analysis. This includes running the injector on a performance test bench at both idle and rated speed and fuel deliveries. This ensures that the injector actually operates correctly under all operating conditions. The final step is a teardown analysis on any injector that does not pass all visual and performance test standards. Parts are inspected for defects using the most modern inspection equipment available. This includes microscopes, electronic roundness and surface finish machines, and even a scanning electron microscope where necessary. This equipment is capable of finding even microscopic flaws and defects. In fact, the scanning electron microscope can magnify the surface of an object up to 20,000 times. It is used to identify inclusions that cause failures and locate the origin of cracks. Here, a sulfide inclusion in a piece of material is shown at various magnifications. In order to preserve evidence of a failure, it is very important that the failed pieces be returned exactly as they were found. If you are ever requested to return failed parts to the factory for analysis, do not clean the pieces or put them back together. Cleaning or reassembling the fracture surfaces destroys evidence which can pinpoint the failure. Wrap the pieces individually in soft paper towels and return them in the same box or envelope clearly marked for identification. Results from the performance, teardown, and failure analysis are compiled and reviewed by both engine and fuel system engineers to determine root cause of problems and necessary corrective action. Problem resolution teams address emerging problems where corrective action is unknown. Let's look at some of the most common customer complaints listed on warranty claims and their actual root cause. The top 4 customer complaint categories comprise over 90% of all EUI injector warranty claims. They are misfire, low power, no information, and runs rough. Each of the above complaints is a description of the problem. Just a few root causes are responsible for most of the complaints. Misfire is the single most common complaint. Several types of problems with internal injector components can cause misfire. These problems typically occur after extended use and usually result in a symptom of an intermittent injector misfire. Through warranty analysis, problem resolution teams identify and resolve these problems. The second most common cause of misfire is no fault. This means that the injector had no visual defects and passed all factory performance tests. In short, the injector had no defects and did not require replacement. The automated multiple cylinder cutout test should help this problem because it positively identifies which injectors are acceptable. However, there are a few which the service technician should look for when diagnosing a misfire complaint. A common cause of misfire is solenoid post-erosion. Arcing from loose connections causes damage to electrical posts on the solenoid. Loose connections result from low torque on the nuts or over-torque, which distorts the threads. The symptom is an intermittent misfire that grows worse as the posts deteriorate. When troubleshooting a misfire, clean and retorque the post connections before replacing the injector. Also do a visual inspection and pull test of injector harness wiring and connections. This is especially important if the problem is intermittent. Problems which are intermittent are generally a poor connection rather than a mechanical failure in the injector. Warning: inspect electrical connections only with the engine off to avoid risk of personal injury. Low power is the second most common customer complaint. There are several root causes of low power. More than 3/4 of all low-power complaints are no faults. These injectors passed all factory performance tests and had no defects. This is a significant problem that should be greatly reduced with the automated multiple cylinder cutout test. The first step is to determine if the power complaint is the result of one injector or a whole set. In the case of a single injector, failure may occur over time, resulting in low fuel delivery on one cylinder under load. A weak, but not dead, injector is sometimes difficult to distinguish using the single cylinder cutout test. The automated multiple cutout test should make identification of a single weak injector very easy. If you cannot pinpoint the cause of low power, a PAR dyno test is recommended for on-highway trucks. It is also important to note whether the low power complaint is recent or whether it has existed since the engine was new. Low power complaints on new engines are usually the result of unreasonable performance expectations, incorrect truck drivetrain specification, or machine misapplication. In other cases, the performance of multiple injectors or the entire injector set degrades. In this case, it is usually difficult to clearly identify a single weak injector. There is no mechanical defect or failure mode that affects an entire injector set. Degradation of an injector set is usually caused by an excessive amount of abrasives in the fuel, which cause premature poppet wear and leakage. Using recommended filtration, such as the Caterpillar high-efficiency filters, can prevent this type of wear. The symptom of poppet erosion is actually a gradual loss of power. As poppet erosion gets worse, leakage of high-pressure fuel past the damaged poppet seat increases, resulting in a gradual power loss. The third and fourth most common causes of customer complaints are rough running and no information. The rough running category is self-explanatory. However, the no information category is more confusing since the claim doesn't list a customer complaint. For purposes of simplicity, rough running combines these two categories. Several types of problems can occur with internal injector components that may cause rough running. These problems result in increased leakage of high-pressure fuel past the damaged surfaces, which significantly reduces fuel delivery into the combustion chamber. The symptom of such problems is usually very low fuel delivery and one or more weak cylinders. This may also occur over an extended period as injector performance degrades. A final problem that may cause rough running is failure of the O-rings on the stainless steel injector sleeve. This typically occurs only at extended miles. Deterioration of the sleeve O-ring seals is aggravated by several factors, including heavy load factors, high coolant temperatures, less than adequate cooling system maintenance. Engine coolant can attack and degrade the sleeve O-rings over time. Coolant can then leak past the O-rings and into the vacant cavity between the inside of the sleeve and the injector nozzle case. Coolant in this area is also exposed to the fuel O-ring on the injector, which seals fuel in the fuel supply passage in the cylinder head. This fuel O-ring is designed to seal fuel and has less tolerance to coolant than the sleeve O-rings. The fuel O-ring will eventually degrade and allow fuel to leak into the cooling system. Because fuel supply pressure is significantly higher than cooling system pressure, the leakage will only be fuel into the coolant for a period of time. This problem is usually detected through normal maintenance, but may result in cooling system overflow. If the problem is not detected for an extended period of time, the fuel O-ring will continue to degrade and allow coolant to leak into the fuel when the engine is shut down. Excessive coolant in the fuel will cause misfire and eventual injector seizure. If an injector is removed and shows signs of exposure to coolant, remove the sleeve and inspect the sleeve O-rings. If the sleeve O-rings are found to be deteriorated from exposure to coolant, install new O-rings on all injector sleeves. If the sleeve O-ring leak was due to a cut, damaged, or improperly installed O-ring, install new O-rings only on that cylinder. No-fault injectors are a minor contributor in the rough running complaint category. Again, the automated multiple cylinder cutout test should dramatically reduce misdiagnosis. All known injector failure modes combined account for about 2/3 of all returned injectors. This demonstrates a significant improvement in dealer diagnostics over the past several years, when no faults accounted for about 2/3 of all returns. Resolution teams are actively working to or have already resolved all injector failure modes. In addition to improved injector design, you'll see a rapid evolution in fuel filtration across the product line. No faults account for about 1/3 of all injectors returned. This category represents our biggest opportunity to reduce warranty claims and improve customer satisfaction through improved diagnostics. This is the driving factor behind the automated multiple cylinder cutout test and the development of improved training methods such as this presentation. You can help reduce no faults by looking for external causes of misfire, low power, or rough running. These include checking injector connections and wiring for clean, solid contact, checking inlet and exhaust systems for restriction, checking fuel supply pressure to assure that pressure is adequate and the secondary fuel filter is not plugged. Finally, make sure customer expectations are reasonable. Some customers have expectations for smoothness, economy, or performance which are simply beyond the capability of an engine or fuel system. In these cases, replacing injectors as defective is counterproductive because it reinforces the customer's impression that the parts were actually defective. This concludes the introduction to fuel system operation and troubleshooting of EUI-powered engines. Understanding how the engine systems operate, how to perform basic diagnostic tests, and where to find service information will help you improve reliability and make it easier to troubleshoot and repair the EUI engines.